We're going to go through the types of reactions, and you should take a lot of notes. So you should already be able to identify the 4 types of reactions: synthesis, decomp, single, and double replacement. We're going to review that, but by the end of the video, you should also be able to write the products of those reactions. The question that we want to answer is that sometimes the best way to clean something is using straight baking soda and vinegar. Not only is it cheap, but it doesn't have any other ingredients in it, and it works even better than things like Clorox or Lysol and things like that. Baking soda, which is sodium hydrogen carbonate, is slightly abrasive, basic solid that absorbs odors. Vinegar, HC2H3O2, is an acid. And what we want to do is write their molecular reaction as well as their net ionic equation in order to explain what's really going on. So synthesis involves 2 or more reactants that combine to form one product. One example could be a metal reacts with a nonmetal. So you can see these are synthesis because the metal is lithium or sodium. The nonmetals are nitrogen or fluoride. But there are other ways. The metal can combine with the nonmetal, but also metallic oxides can form with water bases because they're both technically oxides. So like in the example, sodium oxide and hydrogen oxide can't double replace or switch partners, so they have to combine to make one thing because they would get the same exact thing. If you switch the Na with H, you're going to get them both with O's, right? So in that case, they're going to form a base. Base is always an OH. So you just write the chemical out. There would be 2 Nas, 2 O's, and 2 H's. But we usually use empirical formulas, reduced form, so NaOH with a 2 in the front. Similarly, MgO and H2O are too similar for them to switch partners, so they combine. There's 1 Mg, there are 2 H's and 2 O's. We want to have OH together for hydroxide, so we just reduce it to MgOH2. Similarly, non-metallic oxides that don't have a metal in them are still oxides, so they still can't switch partners with water because they both have oxygen. Instead, they combine to form an acid. An acid has to have an H in the front. So I combined 2 H's, 1 C, and 3 O's with the H in the front so it shows it's an acid. Similarly, in the second example, I combined 2 H's, 2 N's, and a total of 6 O's, but then reduced it to HNO3, an acid with an H in the front. What's crazy is, now that we know metallic oxides are technically basic, and non-metallic oxides are essentially acidic, metals oxides with non-metal oxides form a salt, similarly to basic substances and acidic substances make salt and water. So again, if you have NaO and CO2, you can't switch them because they both end in O, so you combine them. Na, 2, C, O plus O plus O, or Ca, S, O plus O plus O plus O, CaSO4. So hints, look for single elements combining to form one product or oxides. All atoms are together in order of the periodic table with H's in the front from the left side to the right side. Always reduce to form empirical formulas and watch out for diatomic elements like H2 or Cl2. Here's some synthesis practice, one of each. Potassium oxide in water means that you have K2O and H2O. They're going to form a base with OH at the back. There's going to be 2 K's, 2 O's, and 2 H's, but we reduce it to KOH with a 2 in the front. Sulfur dioxide in water is SO2 and H2O. This time you don't have a metal first, you have the H front. H in front makes it an acid. There are 2 H's, 1 S, and 3 O's total, so we're just totaling them. The last one is calcium and fluorine. The calcium's on its own on the reference table. Fluorine's a diatomic, remember Brinkelhoff. And so that makes CaF2, and we're going to talk about perfecting some of these formulas in a future video. Next, decomposition reactions. They occur when you have a single reactant breaking down into multiple products. Most of the time, this results in gas formation. The gases that you should write down somewhere in your notes, but maybe even on your reference table, are CO2, NH3, SO2, and oxygen, and they're going to be subtracted from your original reactant, because remember, synthesis, we added them together. So for decomposition, we're going to subtract out some pieces. Water is usually another common product, but it's not by itself. You'll get water with CO2, or water with SO2. Another thing that you might notice is oxygen's our last bet. You only take out oxygen if you can't take out anything else. So in the first example, MgCO3, when it is heated, it will break its bonds. You'll take out CO2. You can't take out ammonia, there's no nitrogens to take out. You can't take out SO2, there's no sulfurs to take out. So you take out CO2, and when you remove that from MgCO3, you'll have Mg and O left over for balancing or conservation of mass. An example of MgClO3 too, there's no C's to take out for CO2, it's Cl. There's no NH3s to take out, and there's no S in the SO2 to take out. So your only other option is to take out oxygen. What you're going to do is take out all the oxygen. So if you remove all the oxygen, that would be 6 oxygen atoms, realizing that oxygen comes as a Brinkelhoff or diatomic 2s, so that's 3 O2s. The leftover particles are Mg, and don't forget 2 Cls because there was 2 to begin with. In solid ammonium carbonate, you can actually remove quite a few things. You can take out the NH3 that occurs right here. There are 2 of them, so we're going to take it out twice. And you can remove a CO2 because I can see that in carbonate. What would be left over is there's still 2 H's left over and an oxygen to make sure it's balanced. In sulfurous acid, you can take a SO2 because that's the match. If you just remove an S and 2 O's, you'll have H2O left over. See how water comes up as a byproduct pretty often. In carbonic acid, this is probably the most important one we use the most. H2CO3 breaks down into CO2 in water. We're actually going to see this in the upcoming labs. And then solid ammonium hydroxide, you're going to take out the NH3 that occurs, and you'll have leftover HOH, also known as H2O. So see how many times the water is coming up? Exceptions to the rules is if you have hydrogen peroxide, which is the stuff in the brown bottle that you might use to disinfect wounds, that has to break down into water and oxygen. So you're removing your oxygen, but not all of the oxygen, just one particle of it. It's really weird, so we usually just memorize it when we do a lab with it at the end of the year. And compounds with neither of these gases, if you can't take out any of those 4 gases, that means they're just going to break apart. So sodium chloride doesn't have any of those gases. We're just going to break the sodium away from the chlorine to make elements. So hints, look for single reactants and break them down, subtract the gas particles, and memorize these exceptions. Watch out for those diatomic elements such as bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. So some practice, strontium carbonate is SrCO3. Because I see a CO2 kind of hidden in there, I take it out. That's the gas that formed. And the leftover is SRO. Ammonium carbonate is NH4-2CO3. I'm going to take out the ammonia, NH3, twice because there are 2 of them. And I'm going to take out CO2 because I see it here. And the leftover would be 2 hydrogens and an oxygen, which is water. Ammonium hydroxide is heated, is NH4OH. I can remove an NH3 from that and get water left over. And sulfurous acid, I can remove SO2 and get water left over. So you're seeing these gases over and over again. Our third type of reaction is single replacement, involving an element replacing part of a compound it's reacting with. Metals replace metals, nonmetals replace nonmetals. However, since hydrogen forms a cation like metals, hydrogen can also replace metals. It's like a metal, but it is a nonmetal. Okay, so just realize it has nonmetallic properties but behaves like a metal sometimes. So here's an example. Magnesium's reacted with iron 3 chloride. You can see the single replacement occurs between magnesium and iron. So the magnesium used to be alone and now iron's alone because they're both metals. Or in sodium with water, sodium is similar to hydrogen because they're both +1 ions. So sodium reacts with one of the H's. Notice the OH stays at the end. So only one of the H's come off. And you have to always balance and check charges, which we're going to talk about more in detail later. Right now we're just identifying the type. Single replacement here, the lithium is switching with the hydrogen again because they're both similar, both group 1 ions. So lithium and H can't go together. They replace each other. And last, here's another example. Chlorine and iodine switch because they are both nonmetals. So chlorine switches with the nonmetal, so iodine nonmetal is alone. So hints for this, write water as HOH, so you remember to only replace one of those hydrogens in the front. A single element should be on each side of the. Watch out for Brinkelhoff. If a compound is an oxide, remember that was synthesis, not single replacement. All right, and our next type, we have some single replacement examples. Bromine gas and lithium iodide. Bromine and iodide are similar in the same group, so they switch spots. So you can see bromine used to be alone as a nonmetal, now iodine is alone as a nonmetal. In hydrochloric acid with potassium, H and Cl are similar. H and K are similar because they're both in group 1, so they switch places. The K used to be alone, now the H is alone. They don't go together because they're too similar. Our last type is double replacement, and that means that you have 2 compounds trading cations to form new compounds. No change in oxidation numbers occur. They have the same exact charges that they had before. Keep cations first in the formula, so pluses first, then minuses. Usually a precipitate will form, which is an insoluble solid. So a solution of potassium bromide is mixed with a silver nitrate. And what you're noticing is the K stays in the front, but it gets nitrate instead. The Ag stays in front, but it gets the bromine instead. So they switch their ending anion. And out of that, you're looking for something that's a driving force, something that precipitates out. AGBR does that because it's not soluble. So that drives the reaction forward to form AGBR. Charges don't change, so check your charges and drop and swap. Keep cations first in the formula. Sometimes, if you don't form a precipitate, instead you accidentally form one of those particles that form gases. So if you form H2CO3, H2SO3, or NH3OH, those actually break down into those gases that we just saw in decomposition. So if, again, if you form one of these three things, you actually form a gas instead. So you might want to write those down, and I'll give you some examples. When Na2SO3 reacts with acid, at first you might say, all right, I'll switch. Na goes with Cl, H goes with SO3. Fine, that's your double replacement. But if that were true, you wouldn't see anything. What you actually see is gases. So why do you see bubbling occur during this reaction? Because H2SO3 is not stable. It's one of the things that break down into the gas that you know, SO2, and then water as a byproduct. So if you see some of those gases, you have to split them. And now it doesn't look like double replacement anymore because there are three products. But I guess technically it is because it used to be H2SO3, but maybe only for a millisecond. Here's another one. K is now going to go with nitrate, and H is going to go with carbonate. And then that top reaction is your normal double replacement reaction. But when you notice that you get H2CO3, that thing automatically breaks down to water and CO2. So it doesn't look like a double replacement reaction anymore, but it did used to be hydrogen carbonate just for that split second. So here's just a couple of examples where every time you make one of those particles, you actually have to rewrite it as the gas in water. And one more example, if iron 2 sulfide reacts with hydrochloric acid, this is a normal double replacement, right? Fe goes with Cl, H goes with S, and H2S happens to be a gas because it's non-metal nominal. So that is another driving force, something that makes the reaction occur. So some double replacement reactions, barium nitrate and lithium sulfate. You switch the fronts with the backs, and barium sulfate is our precipitate that falls out because it's not soluble. Aluminum acetate and potassium hydroxide, when you switch their backs, you form aluminum hydroxide that's not soluble, so that's a good reaction. And magnesium sulfide and hydrobromic acid, when they switch, they not only form magnesium bromide, which is a solid, but they form H2S gas because non-metal. And so there's two driving forces here. Recall that when you write these, you might also be asked to do a net ionic equation. And that shows why the driving force is so important, why the solid forms. So just to remember, we did ones like this where you showed that when you react reactions, some of them stay ions and get canceled. And the net ionic was showing you how the ion from one chemical and the other ion from another came to form a solid product. But sometimes it's not that easy. Now we know that sometimes instead of forming a precipitate, it might form a gas. So you can see in this example, and you can pause the video if you want to see it in more detail, the H2SO3 actually broke down and decomposed into water and SO2, and those things are what's forming your net ionic equation. Or water and other covalent compounds will not ionize. So if you have water, you're not going to form H plus and OH minus. It's going to stay as a chemical because it's a liquid. Last, weak acids will not ionize, so certain H's with acids. I'm not worried about this right now. You can disregard. I just want to point it out for later in the year. All reactions will work on our exam, but not in real life. So in real life, if I had mixed these two chemicals and formed the products and then it ionized everything because they're soluble, everything cancels. So that can happen in real life, but it won't happen on the exam. Take some time to look over the hints if you can. Last, the question of the video. Sometimes the best way to clean was using that baking soda and vinegar. So what's going on? Baking soda was NaHCO3, vinegar C2H3O2. When I replace, I get sodium with the acetate and hydrogen with the carbonate. But what we just learned was there has to be a driving force. And since I don't see an insoluble solid, the driving force must be a gas. The gas that forms is CO2, right? So I rewrote it again. Instead of writing H2CO3, I wrote H2O and CO2. That gas is what makes the reaction really occur. What I could do now is ionize anything that's aqueous and soluble. So since this is solid, I left it. This is a weak acid, so I'm going to leave it, even though we're going to worry about that more later. This is soluble because both of those are soluble. But water and CO2, the liquid and the gas, stay the same. The only thing you can ionize are things that say AQ. And then cancel. So what's really happening? The reason it's reacting is because this is abrasive, so it pulls up the dirt. This is an acid that dissolves some particles. The particles that you don't want go down the drain. and some of the other particles like CO2 can trap some of your dirt, and then it evaporates off, right? And so you get all your dirt either broken down by the gas formation or the acid. At this point, you should be able to write products of all reactions.